Good afternoon, everyone, and welcome to this post-lunch session. So we will now have a talk by Professor B.N.Goswami. Professor Goswami is an honorary professor of excellence in the Cotton University of Guwahati right now. But before that, Professor B.N.Goswami really needs no introduction, but still for formality, he is a famous meteorologist and climatologist. He is also the former director of IITM Pune. He has been a Pisharoti Chair Professor for ISER, and he is well known for his research on monsoon dynamics. He has been fellows of like Indian National Science Academy, Indian Academy of Sciences, National Academy of Sciences, and the World Academy of Sciences. He has received the Shanti Swarup Bhatnagar Award in 1995. And of course, we can talk many more about his achievements, but without further delay, let's hand over the mic to Professor B.N.Goswami.
Thank you very much, Adway, for that introduction. Let's get started. I'm going to tell you a story about this. This is a story. It's not a very technical talk, but and this title is The Second Revolution in the Weather and Climate Forecast. Actually, it started about 4 years ago when a paper was published in Nature about prediction of El Nino by using the AI/ML method, deep learning method. And so I was quite excited about that and possibility of applications. Then things happened rapidly over the last. Then I started learning about a little bit about AI/ML because I realized that there was a lot of potential about this application in weather and climate prediction. And we started working with one of my students at Guwahati. So we worked on the long-range prediction of monsoon, the seasonal mean monsoon. So during this time with the student, I have still learned a little bit about. I'm still learning. So I'm not an expert in AI/ML, and but I see the potential great potential in applying this to improving prediction of weather and climate in the coming years. And that is why I think this is a new revolution that is going to come. I'm going to give you some reasons why this is a new revolution, because what happened to the first revolution and why the first revolution cannot possibly improve the forecast further. So that is why we need a second revolution. And the second revolution seemed to have just arrived. And it arrived in a bang in 2023 with this paper in Science, which was published in December 23. And this paper was then in 2024, it was considered one of the top 10 news-making science articles by Nature. Nature does every year, at the end of the year, they do publish a series of 10 articles which will make the top news in the world. Like when gravitational waves were published, that paper was published that time. That was one of the top papers, like that. So this considered one of the big breakthroughs in the coming years. So that is how it became. So this paper became very famous. And over last 1.5 years, this paper has been cited by more than 1,200 times. So that is the, that is why I call it a sort of starting of this revolution. So people are really excited about it. So this is the story I'm going to talk about. Now, what is that story? And because of this, of course, the application of these 2024, because of all this, the revolution that parallelly, in addition to application of weather and climate, AI was exploding around this time. AI applications in various different things. And that is why the founders of the AI were given Nobel Prize in 24. So this is a time when the AI explosion became exponential. And that is why they recognized that, for example, Jeffrey Hinton is known as one of the pioneers of the AI revolution, where he introduced how physically guided training can solve physical problems and sort of give insight into the physical problem. And that is, I think, is the basis for all the application of the AI techniques. So to understand this problem, let me go back a little bit and talk a little bit about the first revolution, because without talking about the first revolution, I cannot go to the second revolution. So the first revolution started with this kind of a sort of question. For example, over the last, when I grew up, climatology and the weatherman was a subject of a joke for everybody, like cartoonist. But they thought that so the weather is just by chance. It is not based on great science, and it is like throwing the dice and so on and so forth. But this was going on. But if you look at it, I think you guys have not seen that very much. In the last 20 years, you are not seeing much of it. That in recent times, these cartoons and jokes are not even social media. Not many people are making fun of the weather. Why? This must ask that question. And that is because the weather prediction skill has improved tremendously in the last 2 to 3 decades. And those improvement of the skills have made impression on the people. Now that, well, if the weatherman says there is more than 50% chance of getting it right, earlier they thought there is less than 50% chance of people. That's why they did not have any trust on the weather. But today, I think there is more than 70% of the time the weather predictions come correct, and therefore sometimes it is even short-range forecasts are even 90%, 95%, 99% correct. So therefore, this is felt by community, and therefore the trust on weather predictions have improved. Therefore, all these things, jokes have come down. So I think that is it. Now, how did this, that was the first revolution. How did this happen? This happened because of this. This is, anybody have, any of you are familiar with this figure? No? So some of you are familiar. Because this is the skill of weather forecast and the improvement of skill as with time at a particular center in Europe. This is called ECMWF. This is one of the leading centers on the weather prediction. So this forecast, they started in 70s and 80s, early 80s. They started keeping record. So this is something called ACC, called the anomaly correlation between the weather patterns simulated by model, predicted by model, and actually what happened. So that correlation, if it is very high, like 99.8% here of 3-day forecast, this is 5-day forecast, 7-day forecast, and the 10-day forecast. So 10-day ahead of time, 7-day ahead of time, and 5-day ahead of time, and so on. So 3-day forecasts are almost perfect, today. Almost. That is why our by the way, this is in the extratropics. In the tropics also now we have improved this considerably. And therefore, even in tropics also we have, but not as much as this, but because of the intrinsic problems of the tropical weather is different from extratropics, and that is why we have it is harder a little bit. But still, improvements have been made, and therefore it is felt by the community users. And this is the so earlier you see over the last 3-4 decades, so the skill of forecast in the 80s of 3-day skill, now that much skill is obtained by 5-day ahead of forecast. So more than 2-day ahead, I can make as good as 3-day forecast today. So that is improvement, but it's not. It doesn't sound like very, very much. But that is what that much work is required. That many 2-3 decades of work is required to improve the skill by more than 2 days. That's all. So it's not a very. It hasn't been a difficult problem, but slowly and steadily, a lot of researchers, hundreds of researchers, and lot of funding from government support has improved steadily, and I'll tell you how it has improved, and that resulted in this improvement. And then there was, of course, in the past, there was one serious issue about the data in the southern hemispheric forecast were much poorer than the northern hemispheric forecast in 80s, because southern hemisphere is mostly ocean, no in situ observations, and therefore the initial condition from those areas had much larger error. But then when we had this satellite data covering everywhere, and we started getting very accurate temperature profiles all over the globe, and then things started improving tremendously and almost now correct. So now satellites are giving us enough data to initialize the models over the ocean almost as good as the northern hemisphere, where there are a lot of other in situ observation. But so these are the power of satellite observation. So data has the improvement of data and initial condition and improvement of model. These two things together improved the skill of the forecast. So this first revolution, there is a review paper in Nature a few years ago. It's a very nice paper. I'll recommend any of you to read it. The story is, part of the story is I just from reading this paper. Okay, so I'll not go into great details of that. I normally give another talk for that. But today, I will not talk a great detail of how that revolution took place. That revolution took place through what we call NW, numerical weather prediction route. When numerical weather prediction means solving those equations numerically and using as initial value problem and so on. I'll give you a little bit of hint of that. But the numerical weather prediction today now has reached a crossroad, and it is now not able to go further. And you can see that here. You see, see, over the last 10 years or so, the 7-day forecast are not improving very much. They're staying there, okay? Because they have the potential to go there, but it is not going, not able to go. But why it is not able to go? Because there is some limitation, fundamental limitation determined by the dynamics, the chaotic nature of the system that limits it. And I'll give example of that later. So to understand this problem, you have to understand what is the weather prediction system, numerical weather prediction system. And this system consists of a model which solves the basic equations, the Navier-Stokes equations and the forcing and dissipation, everything that is initialized by initial condition. The initial condition comes from observation, in situ observation and satellite observations. They are then analyzed into regular grid and then used as initial condition. And so these equations are solved into some kind of a discrete grids. So you make a large number of grids, discretized grid, and then in the horizontal as well as in vertical, several layers. So you have a large number of these volume elements where you make the predictions. So that is how the prediction is made. And it consists of basically two different major components. One is the model dynamics, that means which solves the basic equations. But the equations are forced by some forcing and dissipation. So that forcing and dissipation remembers the equations have some adiabatic processes which changes the temperature, but forcing can only change the temperature substantially, and that is what is the which is the forcing comes from various physical processes like radiation budget, moist physics, which involves clouds and latent heat release, and boundary layer mixing, turbulent mixing, aerosol chemistry, and all that can produce effect on the heat budget. And that non-adiabatic heat budget is the forcing. And basically dissipation is through other turbulent processes, how the momentum and heat is dissipated at a very small scale on the surface. So that is the dissipation. So all this dissipation and forcing and dissipation are the physics. So there are two modules, big modules. Among the physics processes, there are many different modules which contribute to this budget, heat budget. Ultimately, the pressure gradient is in the system is driven by the differential heating, and then differential heating comes from all this heat budget contributed by all these physical processes. So, and that is actually in this set of equations. So this is some U momentum equation: the east-west winds, the north-south winds, and temperature equation. So temperature equation has all these forcing. Normally, we don't have too much forcing in the atmosphere on the momentum equations. basically there are dissipation of the momentum, but forcing comes in this in the temperature equation. And so temperature equation produces density changes, and the density changes produces pressure changes. The pressure changes then produces winds. So that is how then they are coupled. And so, so there are a lot of challenges in terms of the depending on the hot resolution, and you have to use, and in the morning article and in Sapna's article also, Sapna's talk also, they have talked about resolution. So I'm not going to get into details. And then of course there are various different physics. All these physics contribute to the heat balance, and the heat balance is the forcing. And so all these things comes and connected to the go into the model equations, and therefore model equations, the solutions of the model equations is the essentially, and so and that the advance in time, and advancing the time is the prediction. So that so therefore any error in this forcing is an error in the model. So, and the forcings come from various very small scale, as Rama pointed out this morning and in the first talk. So all these forcings come from very, very small scale processes, like in cloud formation, but like even in other turbulent boundary layer forcing, turbulent mixing comes from very, very small scale processes. But we wanted the effect on the resolved scale by the model. Model has a resolved scale. Resolved scale is like the scale of resolution, that is 100 kilometers by 100 kilometers, or maybe 25 by kilometer by 25 kilometers. But within this 25 by kilometer and 25 kilometer, there can be very 1 kilometer clouds. And there could be all other small scale processes, including the microphysics. So all that thing we cannot explicitly formulate, and therefore they have to be parameterized. Now that parameterization means, okay, I'll come to that. So this because of the existence of the small scale processes, because the small scale processes cannot be isolated completely because they affect the large scale processes, because they contribute to the heat. So the small scale, as Rama said, the small scale processes start from micron size, micron less than submicron scale particles of CCN to micron scale to micron scale particles of CCN, and then they get through coalescence processes, etc., become millimeter size, and then they form they happen within the clouds. Now the clouds then they get this affect the clouds hitting inside the individual clouds, which are 1 to 10 kilometer scale. Then they get organized into these big tropical cyclones like synoptic scale systems, which are also embedded into the very large scale ITCZ, for example. So for climate, this kind of a scale is important, and the heating over this region we have to estimate. Now that heating will come from all these processes. And so in each of the grid scale, I have to contribution from this small scale has to be estimated. And how do I estimate it? That is what is the parameterization, because I have to understand how, given the large scale variables in that grid box, what do I expect the small scale distribution will be, and what will be the resultant heating. And that I have to figure out, formulate. How do I do that? I have to first understand the process, how, as Rama has shown very detailed way, understand the physics and see how they interact with depend on the large scale. And this dependence on the large scale, you then formulate into a formulation known as parameterization. So this is again almost 15 orders of magnitude. She said 13. I think it can be almost 14, 15 orders of magnitude differences are there in the scales, and they all interact with each other. And we have to so this is what is parameterization. And so this, when NWP first started in 80s, we had very little idea of how to do this. So their parameterizations are very, very simple, very, very simple. Just to give an example, suppose I say when Professor Manabe and all those this Chinese article, they did not even have any forcing, because only dynamics they said. Given the initial condition, how dynamics will change it. But then next came the climate models with other people like Manabe and others, they started doing it. Now they had to have convection in it, the cloud heating, But the resolution was 500 kilometer by 500 kilometer. Still, they had to do some parameterization. What did they do? Madhava came out with a very simple formulation, something called convective adjustment. That means that suppose I know that this much moisture is there, the atmosphere is so much unstable, and so then you assume that all the moisture will be precipitated out. If the moisture is precipitated out, then that much latent heat will be released. So use that latent heat to adjust the temperature profile, distribute it in the vertical. So then it is job, the clouds do that exactly, but in a very complicated small scale. But he said that, okay, forget about all the complications, just adjust the temperature profile and that will be my parameterization. So every time step, if there is a cloud, he will adjust the temperature profile, then go ahead and do the next integration and find out what happens to the stability and moisture and so on and so forth, and then go ahead. So that was very simple. It works on a very large scale, it works to some extent, but then when you come to real prediction of small scale, smaller scale, synoptic scale, it doesn't work. So like that, we have started improving. From that onwards, slowly and steadily, the parameterizations improved. And that is a lot of work that has gone on from about 70s to about 80s, 90s. A lot of improvement in the parameterizations took place. And that is how our skills slowly started improving. So the other challenge is of course, the other challenge is of course the data, the initialized, because these things, there are two errors in the system. One is error that comes from the model, the other error comes from the analysis or the data. So analysis is nothing but the observations come in very different irregular points, right? There are a lot of gap areas, and there are even our land, there are desert regions or Antarctica, Arctic, there is no data. Because, and then over the land also there are many, many forest areas, etc., no data. So all those gaps have to be interpolated, because you need, for solution of the equation, you need data on each grid point. So that interpolation is essentially called analysis. Now, but when you do that analysis, you find that there is a lot of errors, because interpolation has errors, and that when you put in the equation, they will not balance. Because although we know that the system is forced by those equations are the governing equation, that is known reasonably well. But if I put that observations, it doesn't balance. If it not balance, that what the equations will think that that's an initial error. That initial error will then, as the forecast goes, that initial error grows, because the system is very sensitive to initial errors. This is called a deterministic chaos system. So the system has, so we have to minimize that error. Now, how do I minimize that error? So therefore, they started using various different techniques called data assimilation techniques. So these data assimilation techniques essentially try to minimize this initial error so that my initial analysis is more balanced with the equation. So, and that way we are trying to reduce initial error. And that very much depends on the model, because what model itself, what is done normally is, what you do is that you make a very short, take the initial analysis as the initial guess and make a short forecast, 1 hour forecast. Now, if you make 1 hour forecast, it is going through the equation, integration of the equation. Now it is that forecast is balanced with equation, because now it is governed by the equations. Now, assume that now you find out, the difference between that 1 hour forecast and the initial guess. So that difference is the error. Now minimize that error by doing some objective analysis, objective constraint over the whole globe, to minimize the error. That will give me a new initial condition, new analysis, which is little better balanced. And that is how the initial error is reduced. And then therefore that improves the forecast skill. So like that, there are a lot of efforts improve different ways of this objective analysis, different ways of minimizing errors, better and better error minimization techniques, and improvement of the model. So it is very much dependent on the model, because the model forecast, if it has large errors, then again we have problem. We don't know. So as the models improve, this balance also becomes better and better. And that way, our combination of better objective analysis and better models led to minimization of the initial errors. So these two things, one, improvement of physical processes, another, minimization of the initial error through these techniques, both improved your skill. And but still we had sorry. So we still had this issue of deterministic chaos. So to minimize because even if there is small errors in the initial condition, like here, let us say this is my observed analysis. This is observation. Somewhere here is my observed analysis. So suppose this is observation evolved over several days, let us say this way. But if I had my analysis here and I perturbed it a little bit around this, each perturb will evolve in a different way because of the chaos in the system. And that evolution will have a very large spread in my forecast. And that spread gives me error. And that is why actually I cannot make a deterministic forecast, weather forecast at all. So I have to make more of a probabilistic forecast and make a large number of ensemble. That is what the first lecture was telling. Ensemble number is very important. Even for climate simulation, ensemble number becomes very important. So then we can minimize the possibility of error due to the initial condition. And that is why in weather forecast we make a very large number of initial forecast, so that ensemble of initial forecast, at least take the ensemble mean of that. That ensemble mean seems to correspond much better with observations. And that is how you can minimize some prediction error. So all these techniques, ensemble prediction, improvement of initial condition, and improvement of physics, all together led to the improvement of forecast. So basically, basically two things: initial error, and the model error. These are two major error sources, and they can be improved. Initial error can be improved with data assimilation. Model error can be improved by parameterizations and the resolution. I forgot to talk about resolution. Resolution is also important because these equations, when you solve by numerically discrete method, the resolution is very important in terms of error in solution of the equation. The higher the resolution, lesser the error. So by go to higher resolution means you are minimizing the error in the model. So that is required, but higher resolution requires more computational time. So there's some balance we have to make between that. All these things have helped us improving the. So these three things work together to improve this. One is, of course, all these things have been possible because simultaneously with all this research, the computational capability also improved. In 70s and 80s, we had, as was one figure was shown in the by the first talk today, that in 80s, I think only 1 teraflops machines were the top. But today, you are like they're encouraging 21 petaflops. Even in India, we are having 4 petaflops in IITM. So this is the kind of things have happened. But in India, of course, we are far behind. Only last 10 years, 15 years, we have been able to catch up. But this is how simultaneously observed data improved from satellites and all, analysis methods improved, models improved, and then computation was simultaneously possible so that I could go to higher resolution. So all these things contributed to that improvement of forecast. So, however, we are this numerical prediction route have these two things, and as I mentioned already, the in reducing initial error and improving the prediction model, the model errors. But why we have to now talk about the second revolution then? And this is because there are two reasons. At least NWP has reached some sort of a crossroad. And what is that crossroad? As I mentioned, therefore, we need to go to a second revolution to push the boundary of the prediction skills. I believe the second revolution has just started. Now, so I want to talk about the second revolution because I think we in India, we missed this bus of the first revolution because our people in the country, the meteorologists, and did not see the future of NWP. even when I was young, I was growing up, and there was people in my seniors said, an NWP is not going to make anything, so we have to focus on more on observations, empirical models. In India, this was a very myopic view. As a result, we did not focus on model development in the country. We did not train anybody. Neither did we focus on computer development, because computer development globally is one of the drivers is weather prediction. Computer countries always can bank on the weather centers to buy the next generation of computers because they are always buying that. So weather prediction has been a driver of computer generation. In India, there is nothing. India says, हम बनाएंगे हमारा computer नहीं कुछ नहीं हुआ. Because and then it just and China and America then went exponentially growing computer. And when we left behind where we were in 80s. In 80s, early 80s, we got a computer from USA, which was on the par with at that time, but not completely at par, but little bit behind par, but it was contemporary. But then from 80s, we just did not do anything. And by 2006, when I joined IITM, we were almost 30 years behind this race. And that is because of our lack of vision in terms of policymakers, as well as I blame my contemporaries, my meteorologists who did not see this coming. And then when it came, then when I started, then we did not have any people in the country to who could do this in a quick way. So I had to train people to learn model development, and then of course I had to work simultaneously getting computers and so on. So this was a huge challenge. But it has still now within 15, 20 years after I started at IITM, things have changed in terms of progress. In terms of progress, come to a state where we are not able to even progress further, and that is due to the over the past decade, NWP has reached a sort of a saturation, as I have mentioned already, and because also I think there was so there are two reasons I was going to say. So one of the reasons is also on the large scale, the synoptic scale, but the prediction that I have shown by the weather prediction by NWP, by ECMWF, that is mostly on the synoptic scale. That is the weather scale, large scale weather. But on the small scale weather, the problem is still there, and we may not be able to solve that at all, because the errors in the small scale, like the thunderstorms, which are 10 kilometers size, right? And there will be always some small errors in the interpolation and the model, that there will be small errors in the small scale. And because that much there is not enough data, because no matter how much you get, the 10-kilometer global data, where will you get? You'll never get. There will be always some errors in the small scale. And the models will also add to that. So that error will quickly grow, because the growth of errors in the small scale is fastest, and their saturation level is low. But quickly they grow and become saturate, and then saturation means nonlinearity. So once the saturation takes place, a nonlinear interaction between the small scale and the large scale, they cascade the errors from small scale to the large scale. So the small scale error will invade the large scale also and make their predictions worse. And that is exactly what is happening today, because the small scale errors are inevitable. Because of the inevitable small scale errors, the large scales are still being not able to improve the forecast of the large scales. And so this is a fundamental limitation. We may not be able to overcome this by NWP. So we are stuck with this. We have to realize. Now, having realized that, we feel that this is where the AI is going to come. AI can come not only, so AI could improve the large scale through push the boundary of the large scale beyond this. Large scale is also dominated by controlled by this error growth problem. So the error growth is a very serious problem, and we have to overcome this. How do we overcome this? AI may be able to overcome that on the large scale. On the small scale, AI have to do it in a different way. Whereas AI simply then applies some AI technique on the small scale to find the probability, because now you have a lot of data from the weather predictions, and what are the biases or the systematic patterns of how they behave. If we can identify, then we can make better prediction of the small scale also by AI. So I think both ways we should be able to improve and push the boundary of prediction, both of the small scale as well as in the large scale, by using the AI. Small scale, it is already happening. On the large scale, it is already happening. The small scale, we still have to work. I think that is a second sort of downscale application. So, okay. So this is where in 2023, this sort of revolution, I believe revolution started with a bang. And there was these 3 papers that came out. One called, this is by NVIDIA, June 23, forecastnet karke, they call this model forecastnet. Then in July, there was something called Pongu weather. This was a paper. This is I'll come to that in a minute. And then the third one, this GraphCast that I mentioned, Lam et al. So these 3 papers showed that, all these 3 papers showed the feasibility, just like it is like feasibility of improving the forecast beyond the beyond what the best of the numerical weather prediction models did. It was just like like Charney's work. Charney's work said that established the feasibility of making forecast, and this is what I think it has established, that by using AI, how you can overcome some of the problem and push the boundary of forecast further. And what are these? But let me quickly show what are the so why did this happen? So I think there is some reasons, some very, very interesting reasons why it happened in 23. In fact, until 2020, see, to train weather prediction, and we need observations. Train for weather systems change in 1 to 3 hours. Some of the thunderstorms, small scale, 3 to 6 hours, it changes. So we did not have observations of that kind of a resolution globally. Analysis that we have now, we call reanalysis. People have used one of the best model, on the latest model, go back in time and analyze the data all over again, so that we have uniform data over a whole range of time. And that kind of reanalysis, like the European Center has a reanalysis called ERA 5 today. And before that, ERA and other had 6 hourly analysis. That was the best analysis that we had. No hourly analysis was available. But without hourly analysis, we cannot train a weather prediction model, because that will never give me any, even the large scale will not get correctly. So that was one big problem. And as soon as the ERA 5 came out with hourly analysis over more than about 80 years, that gives the tremendous opportunity to train these models. That was the first time. So that was one big important breakthrough. Second breakthrough also happened around the same time, is what is called a 3-dimensional. So far, all the neural network models were 2-dimensional neural network models at the best, and but the weather patterns and everything are 3-dimensional. So the 3-dimensional neural network models were not available, and it happened when this vision transform thing became available. So the 2 things are required, and Earth has a spherical geometry, and the spherical geometry, we have another problem. So there is underlying pattern of convergence of meridian, because those delta x keep changing, and therefore those volume elements keep changing smaller and smaller, and therefore in the solution of the equations have a geometrical pattern built in it. Now you have the data in that pattern, in geolocations given in that way, then what will happen? Then what will happen is that you have a dominant pattern which is geometrically forced. And the pattern recognition technique will find that only. And so you cannot do that. So you have to somehow change it. How do you change it? You have to find a way to transform that into a regular. Mathematically, you can do. In fact, one of these papers, people did that first. First, they did, okay, transform the geometric part into sort of uniform pattern, so that is not a dominant pattern. And therefore, or you find something called vision transform. And you need this three-dimensional vision transform. So this is what made the big difference. And this vision transfer actually made a huge difference. So this paper, in fact, this paper by an Indian called Goswami, I forget his first name, Ashish Goswami, I think. So this paper was initially, he's written an archive article in 2017, and then finally their paper is published in 2015. Then finally their paper is published. So this was in 17. Then paper, I think recently they have published in a proceedings. But even when it was in archive, it was cited by more than 1 lakh times. 1 lakh times. So I recognize that this paper is going to make all time in the last 100 years, all time this is going to come in the top 10 of all times. And that is what exactly happened. And in fact, so this is the recent updated top 10 cited papers of all time. And so this Goswami paper is number 7, I think, number 7. And so over the last 25 years, when all this revolution, AI revolution is taking place, this Goswami paper is number 1. So this is, he did this work. The vision transform has really transformed the way we can do better pattern recognition in the 3-dimensional. And that is what, these are the developments it really made, tipped the tide towards application of AI in many of these. So now coming back to this forecast net, this study was a 2-dimensional pattern recognition. This is where you see, they used, the idea was very similar, used all the data you don't, the whole pattern is not looked at a 3-dimensional pattern, but you took slices of layers and layers of patterns, which are called 2-dimensional, and then find the connected sort of co-varying pattern out of this. So that still they use the same ECMW data for training, and then use something that each lead time they optimize it for one model and so on. And it turns out that this is the skill, SEC skill, high means good, low means poor. And so their model has poorer skill than the NWP model. So it did not go as good as that. But it is also a feasibility study that it is possible to do, but not as good as this. But then when this comes to so when it comes to the 3-dimensional these things, these people did something similar. This is hierarchical temporal aggregation is something similar to what these guys did for the forecast net, where you do one model for each lead forecast. So one day forecast, one model, you optimize this. So basically then what you do is you take the 1 day lag. What is the relationship between if t equal to 0 and t equal to t minus 1? In all the data, I see what is their relationship. So that relationship provides you a pattern, which then you find out how that pattern will change to t plus 1 from this is like a generative kind of thing you can do, because and then that gives me the forecast. So here and then because it's not asking you, given all the data, you are not asking the pattern recognition technique to find out what will happen, what will be my pattern 1 day after, what will be my pattern after 2 days, after 3 days, because then it has to find out all the patterns from all the data and segregate it to 1 day, 2 days, etc. by itself, right? Self-learning. The self-learning might not be able to do it beyond a certain lead time. But if you help them to segregate it first, that is what is called hierarchical temporal aggregation. For each lead time, you aggregate the data and ask them to find out what is the pattern between t plus 1 and t0. And what is the relationship between that one? That the relationship gives me the forecast capability. So that is what it is. So it now improves. And now it improves better than the best of the weather prediction model. So that is how things have started improving. Okay, so then, so I don't want to go into the actual mechanism, but one thing that is interesting, just to make, okay, so in this Pungu weather, they also use that mathematical technique of overcoming the geometrical problem of convergence of meridian. So they had introduced another thing, so that also worked. But the next paper, so these are all, this is this Lam et al. They had this something other thing they call a graph cast model, and here they did not use that hierarchical aggregation method, but they use something called rollout. Here, they're asking it to learn that what will happen after one day. But then it is asking that, okay, so they are using it again, not even asking it to say what will happen after 2 days, what will happen in 3 days, but it is asking that, okay, what will happen in 1 day or 6 hours? Then it says that what will happen after next 6 hours? So given the 6 hours as a new initial condition, what will happen today? So it has to remember only 1 day lag relationship, but what is the variation of that? Depending on difference changes, how that changes, that it has to recognize. And if they recognize that, then we have, okay. So the rollout model is also, this is a 1 day lag model only, but it is trained in such a way that it recognizes small changes in this initial condition, how it will affect the next point. So that is interesting. So it depends on the training method. How do you train it correctly? And it also works very well. So that is why these 2 or 3 papers had set the stage for making further progress. So, and here what they did, they overcome the geometric problem by not going to a normal regular grid, XY grid, but they gone to something called a grid called, what is called, anybody remembers this? Icosahedral grid, where you give some shapes which can be blocks. It's like a blocks which can cover the spherical geometry in a uniform way without gaps. So that is possible by triangular method or by hexagonal method and things like that. But then it leads to other problems of, so you have to completely rewrite your code, and then there are differentials like del u, del x, del v, del u, del y, and their positions of these are all different, how will you do it, and all that has to be properly taken care of. So all that coding problems are there, but this is now has been done by people, and it is now standard, you can do it. So they did it. They analyzed the data into this, and then fed the data into that grid, and then made the forecast. And the whole pattern recognition was also done on this kind of a grid, from this kind of a grid. So in some way, this thing is something like what I look at it in a way that a long time ago, Professor Ed Lawrence, who was the pioneer of chaos theory, had looked at analogs. So it's all your generative models are like analog techniques. So it tries to find out, suppose I give a string of information as the pattern. Then it goes into the all the data that we have, it finds out how many times this pattern occurred and what followed this pattern, or how it evolved, for example, in how this pattern evolved, how it evolved as time changed after that. So this evolution will give me the forecast. So the analogs, in those days, of course, he did not have enough data to find the analogs, and he concluded that there are no good analogs of weather patterns from the data at that time. But now we have so much of data that we can find, and the new techniques are these AI techniques are nonlinear pattern recognition techniques, which essentially can find out these analogs and find their evolution by whatever statistical method that we are using there, and their evolution gives me the forecast. And so this is almost like a analog technique. We should look at that. I mean, we can look at some of these techniques as nonlinear pattern recognition techniques, as analog techniques. So, but there are a lot of criticism about this in the initial stages, and even today, I think, because the problem is that when you do this, find the patterns and see that, okay, this pattern is going to evolve into this pattern. I'm from the data, I'm saying that. And that is my forecast. So this is very deterministic. And as a result, but the actual atmosphere evolves following certain laws, and because and that law is chaotic, and that is what is a real forecast. So if I make deterministic forecast, they may not follow actually the observations very correctly. But correlations have shown that they do follow. But there are some issues that are identified, that when you go to first several, now these patterns do reasonably well on the large scale, but when you do the kinetic energy of the smaller scales within the weather, then its kinetic energy goes down as you go into the lead forecast, like 10-day forecast. The kinetic energy of the small scale go down. That is a problem. That is definitely a problem. So we need to improve that. And that is partly because there is only so much data to train on the large scale data, not so well in the small scale. Therefore, small scale is not predicted properly. Large scale is predicted properly. Large scale means the weather scale is properly predicted, but the smaller scale within them are not very well predicted, and as a result of that, your energy goes down. So but I believe that we should not discard this system because of that, because this has the potential to overcome the problem of the NWP. And therefore, we have to find out how we can improve it. And that is what I think is being done today. So the outlook, the critique is that the kinetic energy goes down, but therefore they say that, okay, I will not be able to really simulate this over a longer period. I cannot convert this to a climate model, because weather prediction, okay, I'm going to 10 days, fine, large scale I'm getting, okay, predictions are reasonably in place, correct places and so on. But if I try to convert it into a climate model, I have to integrate it for a long time. And that time the energy will go down, so it will not be possible to make a climate model out of this. So that was a big problem, and it was still, now it is still a problem, and we have to overcome that. And of course, none of these address the precipitation problem. Many of these, they have all worked on the winds, temperature, geopotential height, and so on, and surface pressure. All those variables can be predicted very well. But when you come to precipitation, even the large-scale precipitation is difficult to predict, because precipitation has much more small-scale variability within itself. And that is what makes it difficult. There is not enough data to train for it. So we might need actually more data to improve this forecast. We'll need more data to further improve today somebody was telling the 1 kilometer global model, cloud resolving model. If we have analysis of that, hourly analysis for maybe 100 years or so, then we may be even able to predict the precipitation much better. So, but most important thing is that we have to convert this system from a very deterministic to more dynamic system. To do that, we need something called a hybrid approach. So where, in fact, that simply happened last year. Into August 2024, one paper that what they did, they combined this kind of a model with a dynamic process, where actually a diffusion model was used to advance the pattern. And so therefore dynamics is there. And also they added a parameterization which was trained on a cloud resolving model output, and the heating tendencies were also calculated from this kind of a parameterization. And that heating tendencies were then introduced. So initial data were then converted into some patterns. That pattern goes into the learned encoder. This learned encoder is essentially converts this pattern into some patterns. This pattern then goes into the diffusion model. And then, then the physics, part of that goes into the physics, and then this physics, the parameterization provides us physics tendencies. The physics tendencies go to the ODE solvers, gives me, and the learned decoder gives me the temperature equation, other part of temperature equation and the tendencies of the physics, then gives me the output. So it is still very interesting and very imaginative way of actually doing it, and still very fast. And so this has become now kind of a standard to go way forward. And this model is, I think, is another kind of milestone in a way to go ahead. So this is called a neuro-ECM, they call it. It is time stepping. It is kind of time stepping. It is some kind of diffusion model, they call it. It is not just like our physical diffusion model. It is something, but it essentially has the same thing. Like a model has, basically our this thing needs to have that non-linearity. So the basic tendency has this, has the inertial term and then these additive terms, right? So those two are the basic fundamentals. And so this diffusion model has that. So now instead of using it on the actual U and V at every grid point, what they use it on the pattern. So I have a string of this data. This is the pattern. Now how this pattern will evolve given the forcing that comes from this physics model. The physics is also converted into everything you can now heating tendency. So instead of making the physics of radiation one parameterization and convection another parameterization, everything from the cloud resolving model, I can train them on the heating tendencies. So I have only one pattern. So it's very easy. So then the computation is also faster. And then you have all the physics in it. So, and that seems to work tremendously well. So it also they used by forcing it by observed SST, they simulated it over some 20 years of period, but it is still not very stable model for a climate. Whether it is still doing very well, climate ke liye, by giving SST as a boundary condition, and then you can still simulate the temperature, the global mean temperature increase and so on. But they mention in fine print that if you make an ensemble of these simulations by these, some of them are not unstable. Some of them are only stable. So it is still there are issues. Some of them just maybe because the neural networks have sometimes can give you if not trained very properly, physically guided way, can give you unrealistic results. So then your climate can become unrealistic, and that is and that happens in some of these. So still, this is a work in progress in a way, and it shows the feasibility. So then came another milestone where you can improve this by using more of a instead of using the ensemble forecast from the neural network model, you can generate ensemble forecast because by perturbing your hyperparameters, because there is some uncertainty in the optimization, so you can perturb the hyperparameters and generate an ensemble model. But instead of doing that, actually you can develop a probabilistic model by probability of these patterns. So if you have given the data at t equal to 0 and t minus 1, what is the probability of a pattern in the t plus 1? So by using all the data, and you develop a probabilistic model of that. And that probabilistic model seems to work. And again, they use a diffusion model to have. So it is also a hybrid model, but probabilistic. So therefore, this is a step forward again, another step forward. So this also can appears to be able to seems to do. Sorry, did I show a result here? Okay, so I think I did not show. I showed the result earlier, but so that is basically I don't want. I don't have too much time, I suppose. So the other thing that happened is another landmark that happened. So far, what everybody was doing is that okay, era analysis is there. So use era analysis also as the initial condition and make the forecast. Then you don't have to do all the actual weather forecast has this analysis part. Is a tedious process to start with. You collect all the data in real time and convert them into the grid, the uniform grid by doing the interpolation and then minimizing the error and so on. So now, but that's already done in era data. So then you not have to do anything. So use that initial condition and then you make the forecast. Convert that into patterns and then make the then make the forecast. So then on the other hand, but so suppose I have to put that into operational work, I cannot do that. I have to get the data and then analyze it and then make the forecast. Analyze in the neural network format and then go do the forecast. So they did that. So they had converted. So they collected all the data that is there. Also, all this so data is available. All the data that comes through this is now stored somewhere. So you take the data on a hindcast mode. You try that out. So they tried it out. So start from not from the analysis. Start from raw data. Do they convert them into grids and then do the analysis and then convert this into from uniform grids. So this is kind of an analysis they do and then convert this data into the patterns and then feed into the model and then do the usual stuff. And that seems to now make, and then they're able to show this happened March 2025. So this recently appeared, and this showed that they were also able to do as good as or better than the best of the numerical models. So now stage is quite so the stage is set for these AI-driven models to be applied into real-time observation weather forecast. And many weather forecasting centers are trying it out on a side, how to do this. Like European Center, they're engaged with these people to another good people are just getting into this because they realize that eventually the combination of this NWP and this is going to be required to further push the skill of the forecast. So what should we do in our Indian perspective? I think we need to think big because we are not thinking, we are thinking on some, we are thinking of some applications in AI, but we're not thinking about building models. But I think we should think about building models also, which may be more suitable for our own or Indian conditions. And we don't even have to change parameterizations, which, see, most of the times, you must have heard Sapna talking about IITM models, how they are trying to modify, right, some parameterization, keeping Indian conditions in mind. Their problem is what, in this NWP model, if you change in parameterization which will suit Indian condition, does not guarantee, because it's all interacting system, doesn't guarantee that everything else over the globe will still remain well. And because they will go down, some of the biases will increase in other places. Once there's biases there, when you do actual prediction, weather prediction, what will happen? The global bias will see as the initial error, and that will kill your forecast anyway. So it is not going to work. Climate maybe, that will exactly what is going on. We should not do like that. So we have to see that we focus on Indian region, but you have to figure out that if I change the parameterization should be such that it will not affect adversely other regions in the world. And that is a challenge, big challenge. It cannot be guaranteed. So, but here, if we train them specifically for Indian regions, the variability, the patterns, we focus on patterns in the Indian region and train them on the global data, how this pattern is related to the global data, then we are not disturbing anything. I am only trying to find out that pattern which will give me the best prediction for monsoon. See, that is what gives me the biggest advantage. And so that is what we can do. So, and so this is why I feel that there is a great potential for not, we have to do two things. We have to build global models, but train it, physically based training for variability of the patterns associated with weather in the monsoon regions and climate in the monsoon region. And that is possible to do. It is not possible to do in a non-WP model. And that is what we should think. And same thing, and the global stage, what is happening is, it is still weather prediction, there is all these developments have taken place, but in climate related work, which is called what I call S2S prediction, the intraseasonal to seasonal prediction, global couple models are required. And in the global couple models, progress is still not that much. And I'll talk about it in the next class, okay? So some building blocks are already there, but we have to think what are the best contribution we can make. And best contribution we can make is, we could make as good as those contributions if we had a division or invested little time in time. But we did not do that. So some of those big impact making work has been done. Now, we need to do, we can still do some important work by doing developing global models, which will be best suited for Indian monsoon region in terms of weather as well as in climate. So I think that is what we need to think. Yeah, see, again, that is the thing I have already said. Okay. So I also feel that that in going over to a couple model, this physics guided, this is something going to the S2S model, we have to be careful because it has the, we have to go, we are going over a lead time of forecast like more than 1 month ahead, or more than the intraseasonal oscillations, maybe we'd like to predict, have good skill up to 1 month ahead. And the seasonal mean, I'd like to have several months ahead, we'd like to have skill. For all that, the self-learning may not be very effective. For that, I believe that this physics-guided training is using hierarchical temporal aggregation may be a better way of doing it. But we should also try to produce some emulators which may be by using rollover. Rollover is also like a hierarchical only, but little hierarchical, which says some self-learning about how the small changes in the one particular lead time forecast can advance to the next forecast. So these two things we should try. So both rollover as well as hierarchical we have to try and see which works better. Okay, so I think I'll stop there and take questions now. And in the next class, I will discuss the seasonal and intra-seasonal. And so we have done some work on seasonal prediction. I'll talk about that. And we have done a little bit of work on building on emulator of assess the variability. We'll talk about that.
Okay, thanks a lot, Professor Goswami, for that wonderful talk. Regarding the questions, I made a plan. So since the next talk, which is scheduled, which was initially scheduled by Professor Joy at 3, since that has got cancelled, what we will do now is, first I will take the questions from the online audience, if any, and if not, then we will take a short break. After that, we will reassemble once with Professor Goswami. So at that time, you can ask him the questions, and then he can also discuss about, like he can give some discussion, have a discussion about some project ideas which he may have, which based on what he said, which based on which you can actually try to frame your project questions. So like for that interactive session, we can have maybe some after some time. Before that, let me see if there are questions online. So yeah, questions. Okay, so there is this question from Ligin Joseph. Thank you for this talk. I have a question. If I understood correctly, GraphCast and many other machine learning forecast models don't explicitly include SST while training, perhaps because SST perhaps because SST evolves more slowly than atmospheric variables. Do you think incorporating SST as an input could help improve forecast accuracy, especially in case of monsoon rainfall that are strongly influenced by ocean conditions?
Yeah, I don't think I don't think SST will improve very much because because of the difference in time scales, but also because even on weather time scales, there is some interaction between SST and the weather variables, especially over oceans, like when a cyclone is there, the temperature changes and that affects the cyclone again. So these things is there. So here essentially the attempt now is to, so in forecasting sense, it may not improve greatly in the weather forecast. But when you come to climate simulations or forecasts like the intra-seasonal, you cannot leave out SST, because then the SST and relationship between SST and the weather variables are very important. So we cannot leave them out. Either we have to use them as two different variables, and then see their covariability, and then that covariability will give me the skill of forecast. But here, whether because because it is very short time scale, I don't think that is going to improve very much. But as we go, as in the next talk, I'll talk about that whether for seasonal prediction and S2S, the intra-seasonal prediction, definitely SST is crucial, and we have to use it. And in principle, we have to make it really coupled. And in the next talk, I'll also give that people are trying to now develop a coupled data-driven model, where actually what happens by the weather variables affect the SST, and the SST changes affect the weather variable. So that also you have to include. So even before that, we can try by taking SST and weather and the atmospheric variables together and look at their covariability, can give us still some good idea about the climate and the intra-seasonal oscillations.
Okay, thank you. And there is one more question from Moti Gupta. How much scale of compute and data do we need to train weather and weather models like GraphCast? Do we have similar ongoing efforts in India? And because as students with limited compute, where can we contribute?
Yeah, that Adway, can you give some idea? Actually, I am not competent to give it, but I have read some of the computational requirement of these. They require some of the GPU servers, like 8 to 10 GPU servers, with and to train them, and with so many, I forget about the total number of cores and things like that. Unfortunately, so we need a sufficient amount of GPU servers to train them, and larger the amount, larger the sort of three-dimensional data and larger resolution, the amount of patterns that will generate will also large, and to process that you need more GPU, and that is what is, I think, missing in our country. We don't have, in the academic organizations, we don't have. In some organizations like IITM, I think has, anybody from IITM here? IITM and NCMRW have sufficient amount of GPU and CPU both, I think, and they can do it. But I'm not seeing any real plan about doing it. But in any of the academic institutions, we don't have. And when people like me, who is retired, who requested for such things, I'm not allowed to write a project to get that kind of a facility, and so we are lagging behind. So it is hard to do that kind of research in the academic institutions, and in national institutions where the facility is there, we are not doing it. So that is our big problem. I don't know if that answers the questions.
So actually, next week we have a talk by Dr. Manish Modani from NVIDIA. So if you have noticed, this forecast net, there was actually developed by people from NVIDIA. So Dr. Manish Modani will actually talk, although he was not part of that paper, but he will talk in details about the forecast net. So at that time, he can give a clearer idea about the computational requirements. He will also actually he intends to give a demo also about how many of these models actually even without actually installing in your system and so on, it's possible to run specific versions of, or maybe limited versions of this. So he is going to give a tutorial on that. So maybe at that time your questions will be answered better. There is one more second part to Moti Gupta's question. Is there any specific reason we needed hourly ERA 5 data with more coarse temporal resolution for training weather models? Because if we couldn't, or wasn't it very useful?
Yeah, definitely. We needed hourly data because, as I said in the beginning of the talk, the weather systems consists from the thunderstorm scale to the lows, depressions, or Rossby waves in the extratropics. So these are the weather systems, right? So they have scales of 1,000 kilometers to 500 to 1,000 kilometers, the big weather system. But within the weather system, we have the mesoscales. Mesoscales are of the order of the 25 kilometers to 30 kilometers, and then going over to 100 kilometers. So these systems have time scales of about sometimes 3 to 6 hours. That's all. And if you have only 6-hour data, 6-hour analysis, then you cannot train the evolution of this, because the evolution is important, because to the pattern recognition depends on the evolution, the memory of how it evolves. And if you have not enough data to differentiate the evolution of the weather pattern, which you have to start with mesoscale. The mesoscales have time scales of about 3 to 6 hours, and that is minimum requirement is 1 hour. Without that, we cannot do this thing. So that is because earlier, that is why if you train with 6-hourly forecast, you will not get any good skill. Because you are not able to see the evolution, and therefore you have missed some of these times. So I think that is simple to understand. And what was the last part of the question?
That only.
Okay, thanks.
So I think if anyone else has any question online, you can type it. Okay, I think there is one more question. Okay, no, that's all. Okay, I think that's all questions we have from the online participants for now. So
I'm not a PhD student. I'm actually a professional. I'm working. I did my master's at IIT Madras in physics. I was an LTVSP student here, but since this talk was related to the field which I was interested in, I just came to attend this. I work on AI/ML. We are like, so in order to predict oil reserves, we are trying to find out what AI/ML methods we can use and we work with seismic data. Thank you.
Hi everyone, this is Dr. Lakshmi Pandey and currently I'm working as a postdoctoral research associate in IIT Kharagpur with Dr. Adway Mitra. And the work which I'm handling at present is groundwater salinity prediction from machine learning.
Hello everyone, my name is Dipan Chakraborty. I am a PhD scholar from IIT Kharagpur working with Dr. Adway Mitra. Currently I am working on making an emulator, climate emulator, or which can roll out to predict, emulate the SST, global SST data. Thank you.
Hello everyone, I'm Yogenraj Patil from IIT Madras, a first year PhD student, and I'm working on using complex networks to study Indian monsoon.
Good afternoon, everyone. I am Sreyashi. I am from IIT Bombay. My work is to understand atmospheric convection from the parameterization point, and later part includes using some AI/ML technique into it, as Sir pointed out. So I thought this course is a good beginner for me to actually get on with that work.
My name is Nitish Kumar. I'm a PhD student in COS ISC. I'm working on effective radiative height and how it changes with different CO2 enhancements and all.
Hi everyone, my name is Shamila. I'm also from COS IIC. So my project is like hemispherical albedo symmetry and its mechanism, how it is working. Ashwin sir.
Hi everyone, I am Shrihari. I'm also from COS IIC. So I'm just finishing my first year. I'm probably working on coupled atmospheric oceanic models.
Hi everyone, my name is Tatsat Solanki. I'm currently in COS ISC, working a PhD student under Dr. Venugopal sir. I'm working, I might be working on monsoon variability. Not sure yet. Searching for the subject right now.
Hello everyone, my name is Edwin Borison. I'm also from Chaos ISC Bangalore. I'm under Professor Jay Sukatme, and my major area of work is geophysical fluid dynamics, and more specifically, if I try to narrow it down, it will be on the propagation of Kelvin and Rossby waves and its effect due to the Indian monsoons, and in future, what is the prospect of AI and ML in this propagation and studies. Thank you.
My name is Jim Thomas. I'm a faculty member here at ICDS. I work on geophysical fluid dynamics a lot, and I use a lot of data-driven models and neural nets for my work.
I am Chitranjan Pandey. I just completed my PhD in mathematics from IIT Kanpur. There I developed some numerical finite volume schemes for Navier-Stokes equation and some other PDs having diffusion and convection dominated properties. And also being a finite volume expert, I explored some NWP models, NICAM, which is based on finite volume method on icosahedral grid. I have some expertise in that direction in HPC and CPU, GPU, everything. Then by the time I just like attempted 2-3 problems in NWP, the time has come that I have to switch to data-driven problems, data-driven methods. That's why I'm in this workshop. Thank you.
I am Prithvi Devi. I got my master's in atmospheric science from Central University of Rajasthan. I worked on AML modeling in hydrology. Hydrology. Stream flow.
Hi everyone, I am Ashwin, and I am work with her like hydrological modeling using MAML for stream flow projection, and yeah, that's.
Hi everyone, my name is Manu Jangit from Central University of Rajasthan. I just completed my master's. In dissertation, I worked on lightning density prediction using machine learning.
Hello, everyone. My name is Anirudh. I just finished my master's a month ago, and now I'm working on a project with Dr. Akshay at the Climate Studies Department in IIT Bombay. I'm working on seasonal trends and co-occurring features of extreme rainfall events.
Hello everyone, my name is Yash Tambe and I'm a first year PhD student at IITM Pune. I'm working under supervision of Dr. Bipin Kumar and my research topic will be cloud microphysics.
Hello all, I'm Shreyas. I just finished my master's at IISA Pune and I'm working on how stratospheric aerosols affect the monsoon.
Very good. Good afternoon to everybody. This is Rahul Kashyap. I recently submitted my PhD at IIT Kharagpur in Earth System Science. I largely work on land-atmosphere interaction, particularly carbon-water coupling, with using satellite remote sensing data and some machine learning algorithms for like implications for carbon dynamics and like overall sustainability for India and some global weighted region as well. Thank you.
So hello everybody, I am Triparna. I am from IIT Kharagpur Koral department. I work under Dr. Nairita Pal and we plan to explore data-driven methods in studying ocean vertical mixing. Right now I'm using a technique known as dynamic mode decomposition. So we plan to do so that in future. Thank you.
Hello, I am Varsha from Central University of Rajasthan and I'm working with Dr. Chinmay Malik and we mostly work on aerosol cloud interactions in the desert environments.
Hi everyone, I'm Rinu Raghavi from IISA Pune. I did my master thesis in IITM Pune and my research was on cloud microphysics and its parameterization.
Yeah, hello all. I'm Naveen Kumar from IISA Trivandrum. I recently completed my master's in physics. And in my master's, I worked with Dr. Vishnu in building data-driven models for forecasting monsoon low-pressure systems. And in future, I'm looking forward to exploring techniques to incorporate physical equations within ML models. And yeah, that's my main motivation to attend this program.
Hello everyone, my name is Uday Bhattacharya. I am first year PhD student from Dibrugarh University, Assam. I'm currently working in aerosol cloud interaction. Probably I'm finding my objectives actually.
Hello everyone, my name is Pankaj Sharma and I am from CSR 4th Paradigm Institute, Bangalore. And I will be exploring the impact of land surface processes on extreme rainfall events using mathematical model simulation.
Hello everyone, myself Nishant Gautam and I am working at IITM Pune under Dr. Subodh Kumar Saha and I am working under land surface processes, specifically focusing on extreme events like heat waves and droughts.
Hi everyone, I'm Siddhant Tarya from IITM Pune. I work with Dr. Amita Prabhu. I work on influences of high latitude modes and cryospheric sea ice on global monsoon systems and western disturbances, Himalayan snow.
Good afternoon, everyone. I'm Swadesh Mahapatra, and I am doing second year PhD with Dr. K.C. Gowda in CSR 4th Paradigm Institute, Bangalore. And my thesis will be on developing ensemble framework for better prediction of urban high impact weather events using some like dynamic AI model of NCMRWF, NCOMR, and HRRRDA.
Hello everyone, my name is Deepak. I'm a PhD scholar at IIT Roorkee. So I work on atmospheric moisture transport and related extremes, especially hydrological extremes. So I'm currently exploring data-driven methods as well as physical models. So that's my motivation to attend this talk.
So hello everyone, I'm Pooja Bolle. I'm a master's student from Pune University and I'm doing project in IITM on using NWP models for heat wave predictions.
Hello everyone, I am Pranita Indore. I am a second year student of MTech at the Savitribai Phule Pune University, and I am currently doing project in IITM Pune, which is on CMIP6 climate models.
Hello, I am Pooja. Currently, I'm doing my PhD from IIT Bombay under the supervision of Professor Subimal Ghosh. So, I'm working on improving the rainfall forecasts for Mumbai at daily and sub-daily scale. And further, our work focuses on giving real-time flood information as well as flood forecast. Thank you.
Hello everyone, I'm Manali and I'm from IIT Bombay. I am currently working on precursors, understanding the precursors of heat waves and especially focusing on the moist heat waves, which is what it gets triggered by. And and also I'm trying to understand the mechanisms and dynamical aspect of it, and also look at these events in land atmosphere perspective. Thank you.
Hello everyone, my name is Usman and I am currently a PhD student at IIT Bombay. I'm working under Professor Subimal Ghosh. My work involved mainly soil atmosphere interactions. I'm also working with using deep learning models for downscaling soil moisture and making predictions for soil moisture at medium range and weather forecast scale.
Hi everyone, I'm Agastya. I'm currently working in the math department in ISC under Professor Manjunath Krishnapur.
Hi everyone, I'm Shruti. I'm a PhD student at Indian Institute of Science, and I work on monsoon dynamics.
Okay, since most of you or almost all of you are from the art science background, so I should also ask. So, how many of you have done at least one project which involves some amount of AIML? That is where how many of you have done at least one project in which you have implemented something related to AIML? Okay. And how many of you are completely unfamiliar with AIML, that is, have not done anything related to AIML at all? Okay. Okay. So, you may have face a little bit of challenges in understanding some of the talks, but I hope that
how many of you actually have hands-on experience on climate modeling or weather modeling? What kind of weather modeling you have done using? Huh? Okay, okay. Okay. And have you been involved in actual data analysis related to like how the initial conditions are produced and things like that? No, no. Okay. Anybody? Huh? Okay. Nikam, Japanese model. Okay. 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 Mm. Okay. Okay, good. Some experience. So I think the other thing that let me get a sense of how much So many of you who are working on weather and climate, what kind of work you have done on understanding variability or using a lot of model outputs to understand the variability or something like that? That kind of work anybody has done? Because I think AI application is all about handling big data and how physically meaningful way you can apply that. That requires and because you are all from, most of you are from the weather and climate background, at least you should have that much in sort of exposure. If you have, then it will be easy for you to get into. I think people from purely from computer science background, they have to learn a lot to handle this data and how to visualize the data. So how many of you have any experience on that? That is, yeah, that is very important. I think see, essentially, most of these are, most of these AI applications are essentially signal processing. And your gravitational signal processing is gravitational waves is a signal processing problem because it's a very small signal embedded in a large amount of noise. The climate and weather data is a signal processing problem. The pattern recognition that we are going to do is a signal processing problem. You're asking the code to figure out what is the relevant small signal amongst this lot of noise that is there. Because in the weather data, or climate data, we have a lot of noise because of the natural variability and perturbation that is there in the atmosphere. All kinds of clouds are forming, it is hitting the atmosphere in very small scale. That is like a small perturbations all over the world, and that is causing a lot of noise in the data. And data is embedded, all that is embedded in your data. Now from that, I have to figure out the large scale signal out of it. It is a signal processing problem. So that signal processing, and in many of the meteorologists do all the time signal processing, like especially when people are working on climate. They are beginning to, they have to find out what is the climate variability, what is the pattern of climate variability, what is the amplitude, what is the period of climate variability. These are all signal processing. So that is different times you have done here or there. But what this AI thing, you have to understand that, you have to keep in mind. This is a signal processing thing. How do I, how this, and it's all about variability. Variability of patterns. Now first, these guys have to identify the patterns, and then they have to understand the variability. And once they do that, and what technique we use, and then those are the techniques that goes into inside your AI modules, and that is what you have to figure out what is the best. And so I think if you follow from this kind of fundamental principles of concepts, then I think you will be able to, once you are familiar with the data, because climate, anybody, if you are working in climate, you have to, today, you have to look at data, because you have to test your, forecast or anything that you want to, suppose even if you are studying a process study, then the process problem, you have to validate with data. From data, you have to extract that signal and then compare it what your theory or modeling has shown you. So this kind of things and always requires this signal processing in some way or the other. So with that, I think you. So I think you are, but you have to have the interest in because you will have to learn few things. And then spend some time to learn that. And that is why, unless you will be able to spend some time and have interest in, then it will not work. So after, maybe we'll discuss this after tea, a little bit of break, small tea. So, so what I would like to do is that pose a question and see how many of you could think about whether you can think that you will like to get involved in this and you can take up such a problem, and will the resources will be there, or whether your time and resources will be there, whether your system where you are working will support it. All that question is there. So I'd like to see, because I feel that you see, person like me, I cannot do alone because I have not much resources. But I have some ideas. So those ideas, if we can, I need somebody to take up those ideas. And I think because they will make some good contribution, I believe. So let us see. Let's have some tea and then we'll chat on this. I have not prepared anything. I'll just go to the board and I'll say a few things and then we'll see. ठीक है? Okay. Okay, Adway, shall we break? Okay. So before I, because what I want to discuss requires a little bit of more background that I had given in the last lecture. So it is more related on the climate prediction or the seasonal to intra-seasonal prediction. So in the intra-seasonal prediction, it requires essentially in a coupled system, ocean atmosphere system. So how do you do it? So we need to have a either coupled, really interacting coupled system, or at least all the variables are coupled, at least co-variability we can do. So far, I think in the next talk, I'll give you the sort of history of what is the development that is taking place. So if we had that talk, then maybe what I'm going to propose is towards the end of this talk, I was going to propose some development. I'll just open that up and then come back to so main problem is that we have applied. So our problems, what are the problems on seasonal, specifically for monsoon prediction? So far, the dynamical models of the, so there are two issues here. One is the prediction of the rainfall, seasonal mean rainfall over the whole India or everywhere in over India, the seasonal mean, one season in advance or many seasons in advance. So that is one big problem. That is what we call the long range prediction by IMD. And for dynamical models do that. But at least, but the skill of those dynamical models today is such that all this is a correlation between that skill of dynamical, an ensemble of various different dynamical models under what is called a whole series of North American multi-model ensemble. So there are several different models. They made predictions up to 11 months, 12 months in advance, then correlated with observations. Only rainfall averaged over India. The whole only seasonal June, July, August, September rainfall averaged over India. Even that number, if I correlate with what is predicted and what is observed, the correlation is just about 0.5, just barely useful, and that is the status in 1 month in advance. But then like May month, if I make predictions for the next June to September, mean, that is my correlation. Then suppose I make for 2 months in advance from April, initial conditions, then that is my forecast. That forecast then, as you go in lead time, it just decreases and becomes useless, statistically useless after 2-3 months. So there is no, that is the skill, that is state of art around the globe, best. And we are not able to improve it. It has not been improving very much. And IITM, we have done a lot of work and made it little bit improvement, 0.6, and up to about 0.6 and 0.65. But then by one particular model, but if you take different models, ensemble mean, that will still come down a little bit. So people are trying to make that improvement in some models, but we are not able to go beyond 0.65 and all. And that is what is the kind of becomes a limit. So that is what I'm saying is that seasonal prediction is being limited by these models. Now, how do we go ahead of this? So to do that, we have done some work by using a certain method. But we actually did this. I'll not go into it, otherwise it will be just everything repetition again for me. But we first did this in a sort of systematic way. First, we wanted to understand: it is impossible to really go to predict, or is problem of the error growth problem? If there is there predictability beyond 4 months, 6 months, or not? We don't know, because there are all the predictability, there is physical basis for predictability beyond 3 months, 6 months, or more than a year was not available. So we did a very serious research work, and one of my students published this paper. And then we established that there is a predictability beyond this, and and the physical basis of that predictability was established. I'll talk about that more details. But with that basis, then we used sort of a CNN model. Now we found that there is a predictor which can predict this better, even up to longer lead. Monsoon has high predictability, even up to 18 months to 24 months lead, very high predictability. And we established that. Having established that, so for many of these things, when you use, you have to have a physical basis to expect that there is skill going to be there. So for that, you have to establish that predictability of that system on seasonal time scale. So we established that. Having established that, and we applied one model which could actually make this prediction, and we showed that this is the result. So here we could show that the prediction skill by the model is actually increases with lead time up to 18 months or so. So even at 18 months, you get a very good skill. Compared to the dynamical models, which are going down. Dynamical models have that intrinsic limitation, and we have physical arguments why it should be happen and so on. But this is very simple model, because of our limitations. We have used data from the CMIP6 models, outputs from the past, many such, some 35, 40 models. You train them on that, and then improve their skills by what you call transfer learning with observations, and then you make the predictions on an independent set of data. So all that is done. So, but this is still, we want to go beyond that. What is the beyond that we have to do? We have to go to the distribution of rainfall. So we need to go beyond the distribution of rainfall. It is just one number, right? So I need to see how the distribution of rainfall is predicted on a seasonal mean time scale. So that requires a three-dimensional model, because then only we will be able to do that, right? So that is the problem that we'd like to do. And for that, we can develop. So here, our whole philosophy has been a physics-guided training, so that it can, for each lead, we are devising a particular model, and then this is called what I call this hierarchical temporal aggregation. That method we use, and for each model, we train it so that it can catch the most important, the dominant relationship between that lag. So, so that way we have been able to extract the signal better, we believe, and we have physical reasoning for that. So, so question is now what I want to, but now we extend the next question is, so there are two issues. One is make seasonal prediction. The other issue is make intra-seasonal prediction. Intra-seasonal predictions this may require, this problem can be solved by using building a sort of monthly mean climate model. And then even if I make a monthly mean data climate model, then even that may be able to do a good job. But when you go to intra-seasonal prediction, then I have to do daily predictions, because then my goal is make daily models, or up to about 35, 40 lead, so that these intraseasonal things are like monsoon intraseasonal oscillations have period of about 40 days, 35, 40 days, right? So these oscillations have the active break cycles. So these, I want to take an index of these, this intraseasonal oscillations, and then and then predict that index, just like MGO predictions. I think some of you maybe predict. So this MGO prediction. So use that and develop an AI similar to this. Develop a model which will give me prediction of the monsoon intraseasonal oscillations up to a lead of 35-40 days, and see, compare that with observation and skill how my skill improved. Currently, that problem shows that with all the best of the models, I had actually prepared a few slides. I somehow lost it. I could not figure. Next time when I am I have to see where it is. So, so the current status is by the European Central Model and all that. They are doing these predictions. The skill is about 20 days maximum. The correlation of this index of these intraseasonal oscillations and compare with observation is up to about 15 to 20 days. We need to improve that. If we can improve that over 30 days by doing this, it will be great. And that I think is possible. And so my one problem that I want to do is to develop a intraseasonal prediction system from this. And so how do you go about it? So do that similar to this. So this can be done. Again, I have been limited. This is a low-hanging fruit that has been going on for a long time, but because of lack of data, and we have done some preliminary idea. Just like we did predictability studies of this, and the predictability also has to come from somewhere. For the intraseasonal oscillations, that predictability will come from, again, its association with SST. So on intraseasonal time scale, we looked at correlation or lead-lag correlation between daily SST anomalies and the intraseasonal oscillations. And we found that it has a very strong large-scale patterns of SST which are connected with this at different leg. And so we have a there is a paper by Suhas et al. So we have an index which we did. It is 214, I think, in climate dynamics. There we had developed an index. So I want to take that index. Okay. And there are two indices. So these two indices give me.
This is the MISO paper, is it?
Huh?
MISO paper.
This is a MISO paper, right? MISO paper, right? Two indices. So I have all the sort of required background that is ready. But if somebody is interested, we can work together and do this. So what we are planning to do is that first you establish this, we do this lead-lag correlation, etc., and the basis for the prediction, and then go and train this. So this indices will take the indices and do lead-lag correlation with the SST. So we have these SST patterns. Now daily SST data is we can from from observations. The era itself has its own SST data. So daily SST, we can take daily SST anomalies. We can train on them. We also have observed daily SST, not too much, because only from about 1979 we have some data. But ERA, again, we can use ERA data itself to train on daily SST. Then we can use more data from CMIP6 models, some high resolution CMIP6 models who have daily SST data, and use their daily SST data as to train, and then validate it with transfer learning with ERA 5 data. Okay, so like that, similar to a process like that, then you build build a model at every 1 day lead, you make 35 models for every lead, and use predictions for that. Then you have these 35 lead predictions, and with observations, also you have similar data. Then you correlate, then you find the skill. So the methodology, physics behind this is more or less it's sort of clear, and all we need is to do. But this requires a certain amount of, because of the daily data and all this, it requires more training effort. So it will require a little bit of more computational problem, and that is the main problem. That is, but would anybody of you be interested in that, and will you have some computational resources to do that? Otherwise, anyway, I'm going to do it at some point of time, but I don't have the competence and resources at this point of time. But we'd be happy to discuss anybody who is interested, and if you have interested, we can collaborate. We can discuss further what we can do. So that is one problem. The other problem is also, I have that problem that we can think about is actually making a 3-dimensional model for seasonal prediction, which is again trained specially for monsoon. As I mentioned in the earlier, that we cannot fix the parameterization specially for monsoon and hope for the best, but here we can still do it better. Because just like we did for all India, suppose including the rainfall data also, and several layers like SST, D20 maps, and surface temperature, surface temperature at 2 meter height. Then you have winds and temperature at 850, then winds and temperature at 200 millibar. Like that, you will have about 10 variables. Then you find the coupled, the train to find the coupled variability of the patterns, and then predict, sort of train them on variation of the rainfall patterns, because seasonal mean rainfall patterns. So this is a seasonal prediction model. So I have the seasonal mean rainfall patterns of the monsoon region, that time series will train on this these data, rainfall and all the 5 variables, and then produce a prediction for all these variables, including rainfall. So I think that is also possible, but it will require much more computation compared to even the intraseasonal stuff. But I think it is doable. All you need is some help may be required in terms of making it efficient. So making system efficient will require input from computer science people. But sometimes we are stuck with, many of these things, the success depends on how you use it to make your application, AI application more efficient, more computationally efficient. And that depends on how you apply it. And then I may not be the best person to do that. So I need some input on that from computer science people. If anybody who can give some. We will of course start with whatever I know, but maybe in the process it will somebody has to help us to make it more efficient.
I have one point here. So these models like these GraphCast, ForecastNet, etc. Like, has it been studied how well they do specifically in the like Indian monsoon? I mean, they are of course aimed not for seasonal forecasting, but for or not even sub-seasonal, but they are like for like hourly forecasts and so on. But during the specifically over the Indian region and during the monsoon season,
Right.
how good is their performance?
So the point is that what will you try? What is validation? So basically you have to do weather. And what is the weather in the monsoon? Monsoon weather is lows, depressions, right? And sometimes tropical cyclones. Tropical cyclones, they have validated on some area, and those even in North Indian Ocean, I think they have validated a couple of them. They seem to be okay. Lows and depressions, I have not seen any validation of this monsoon region, the statistics. I was talking with somebody this afternoon, but I have not seen. So, and especially, I think nobody has validated how the extreme events in the daily extreme rainfalls are predicted. That will be probably bad anyway. That we probably cannot. But I don't think it has been done. I won't think that that will be very fruitful. I think conclusions are more or less to be because there no rainfall is there, only winds and temperature. How useful it will be. So for monsoon, it is not a very useful product because unless we have rainfall information, monsoon is no use. So that is why I think not much of a validation effort has been going on. So, but one of the studies, as I mentioned, has started rainfall, which I don't think anybody has evaluated so far. That is one possibility that somebody can look at carefully.
So there is this concept of teacher-student models, right? So like you have very in neural networks, there is like some very complex models, like let us say these GraphCasts and forecast nets. These are of course computationally very expensive models. Now, but they are aimed for like a large region, let's say for global, global scale weather forecasting. Now, sometimes we may think of building an emulator for these models at a much smaller scale. Let's say I'm not so interested in global weather forecasting, but I am interested only for the Indian region. I want to do monsoon weather forecasting. So like one thing that can be done is we first train a student model which is basically a scale, like a much smaller version of these kinds of models. And so now what happens, the benefit of doing that is whatever the skill these models have in making forecasts, that can be transferred to this student model without, although it should be on that particular domain, which in this case is the Indian monsoon. It will have developed that skill. But now, once that skill has been transferred to that student model, then we can incorporate other aspects to it, which is not there in the original model. Like we just mentioned about the precipitation, then about like we can try to expand it to say sub-seasonal forecasts and things like that. So that is one rough idea which I have.
I think that's a good idea. I think the third problem that I was thinking is as an emulator model, which need not be specifically trained for monsoon, but it will be basically emulator of the whole climate, just like we have done for the SST. Now the SST model is a good example. Now suppose I could replace that the whole thing and combine it with precipitation and monthly mean again, let us say. Even monthly mean is okay. As far as but now over the whole every grid point, right? So including precipitation, SST, D20, and some winds and temperature in the atmosphere. So we will have maybe 5 or 7 layers of things. Can we make an emulator just like that? I think it is possible, because there will be emulator will be fully coupled, but it will still be coupled variability emulator, and the coupled variability emulator, if it is as good or better than the SIMIP6 models on which it is trained, then just like our SST model, then it will be suitable for seasonal prediction. Then we'll make actual prediction using that. So then I can once you have the emulator and show that okay, his variability is capturing correctly for many years, then use that to actually make prediction, because you can train it on that variability, and then you can make predictions. So I think that will be that is the way to go. I think that's another way to go. So there are all these possibilities exist. We need people working on it. Not enough people working on it.
Yeah. So thank you for these ideas. So would any of the students want to comment anything on related to this? I mean, it's not that you have to give like some or
Yeah.
could answer the questions right away or propose some architecture right away, but any comments or observations which any of you may have, please feel free to share.
Any thoughts, any, sort of idea?
I have a thought. Like the GraphCast models and all the AI models are very heavy to train. So why this kind of research is not being happened that to prune or to simplify this kind of models like teacher-student network? This kind of climate, AI-based climate models.
My suspicion is when you go to complexity like multivariables and ocean-atmosphere interactions, it may not work as easily as it does on a very simple. My suspicion is that. Also,
At least optimization can be done, right?
also, I think so far because their goal was simply prediction at this point of time. Mostly, see the emulators thing has not progressed so much. Even for weather prediction, atmospheric model, the emulator is not so a good emulator is still not available in a three-dimensional sense, right? So that they have been limited to prediction models, not the simulation model. So the prediction you can get away with in a short lead without this thing, but emulators have to be good to simulate
For a long term.
for a much longer time. And that hasn't happened because it is more difficult in a way. So we are lucky to be able to do at least for one variable, which that is why I feel that that is a good contribution. So I suppose that is the issue. And probably they have not tried it because they have not, I think, focused mainly on, that is where there is a scope now. You see, the initial focus was to weather predict. How can we replace the dynamical weather prediction models? See, we started asking, can we replace CMIP6 model for climate? So they started asking, can I replace the dynamical models for weather prediction? And they succeeded in to some extent. And so I think they have not, nobody has done this in that way. That is why, and to do that also they required a more complex model. The simpler model will not work because of the variables involved, so many variables that are involved here. So I think that is my gut feeling. That is what.
Thank you, sir. Thank you.
Sir, could you please explain that why does the CNN
Little bit louder.
Could you please explain that why does the CNN model is showing a lower forecast scale as compared to the other models for initial couple months, as the figure you have shown?
Which model? Which model?
The CNN model, the deep learning model which you are showing in the paper right now.
Actually, very good question. Very good question. Oh, sorry, I got it out of this. I don't know. Okay, so so very interesting that that you have to read our QGRMS paper, the predictability. So it turns out that the monsoon prediction at a short lead is it starts from May or April or May. So it is affected by what is called the spring predictability barrier issue, and therefore predictability at the short range is high, okay, low because of that. But what happens if so at longer lead, the growth of error depends on two things. One is the first growth of errors, which affects this, the associated with the short lead, and the slow growth of errors, which affects the longer lead. by the shorter, but longer lead, it is physically determined by slow growth of errors. There are two types of errors in the coupled system. One grows because of the coupled instability in the system, that is a fast growing mode. Another growth of errors, it says longer lead. We had done a lot of work in the past to demonstrate that. So and then we found that from data also that itself can be seen that there are these two types of errors are there. And the fast growth of errors affect the short lead forecasts. Then what happens that because the atmosphere is governed by the longer lead, slow growth of errors, which is determined by this 4-year oscillation, and so that particular oscillation determines the growth of errors on the longer time scales, and that coupled with the what you call phase locking of these errors with the annual cycle. It turns out that about 18 months, the forecast error will be minimum. It will be such because of this combination of this thing, because the growth of errors and the sort of phase coupling with the annual cycle. Monsoon is always fixed in June, July, or September. So it is always sort of phase locked. The growth of errors are also phase locked because of the spring predictability barrier. So that time the fast growth, the later time it is slow growth. So as a combination of this, it turns out that forecast error becomes much smaller at longer lead time. And at about 18 months, it becomes the smallest. And that is why the highest predictability. So it's a combination of how error grows in the system and how it is phase locked with the annual cycle. That determines that at the initial time, that phase locking is sort of, it is completely determined by the spring predictability barrier and the fast growth. So you cannot do anything about it. And then but still then, if you take SST, I cannot still make good prediction at 18 months. That is because SST has some high frequency noise built in it. And that is because atmosphere affects the high frequency noise, like weather disturbances, the intraseasonal oscillation produces a stochastic noise in the SST. And the SST cannot get rid of this. And so as the forecast lead increases, the stochastic noise makes the skill poorer and poorer. But that thing, it is not just the spring predictability barrier, but the stochastic noise kills the SST skill. On the other hand, the D20 is not affected by any stochastic noise because it is in a deeper level. So these high frequency things cannot affect. So it sort of filters out the stochastic noise. As a result, it is affected only by the oceanic large scale growth of errors. And that is why it is able to capture that in the good skill in the higher. So these are all a lot of physics behind it. So I think we are beginning to understand that now, that it took quite a lot of time before we could actually understand this. Thank you.
Thank you, sir. But I just have a doubt regarding when you said that we are trying to predict intra-seasonal monsoon predictions during active and break spells. We know that there are two major school of thoughts which have a problem. One is telling that the soil moisture is driving the precipitation. The other is telling the vice versa. Now, in such a case scenario, when we are trying physics-based models to do this, can we use the coupled simulators, coupled emulators for both soil moisture and precipitation to get an accurate data? Because when I'm taking physics-based information, most AIML data, they don't take into the consideration how local processes also changes. But if I'm doing validation for inter-seasonal predictions or for a longer range, local data also matters, right? So what is your take on that?
Yeah, so I think that's a good question. But my suspicion, my thing is that there is not enough good soil moisture data to train. because not consistent soil moisture data, and so it will be if there is we can get good data on soil moisture because SST is something that we can see that ocean atmosphere interaction affects the SST on intraseasonal time scale. We know that pretty well, and that is the kind of signal we get from the lead lag sort of correlations with the daily SST and the intraseasonal indices. So like that, if I have to establish some basis for, I need good data to see what kind of correlation exists on a spatial scale, so that that spatial pattern I will be able to use as a driver for the prediction. And so so far, I don't know if we can get enough data on that, because that is not enough good data. Otherwise, and the data should be consistent with the SST and the other fields if we use any other fields like winds and all. So, or at least if we have enough data on to validate sort of the relationship between them. So my suspicion is that at this point of time, that is why we are thinking I will start with SST and see at least how does it work. And then my gut feeling is that SST itself, or maybe SST plus some circulation which is connected with SST. Like intrasolar atmospheric oscillations and the SST are linked through this ocean atmosphere interaction. So therefore, if I the daily wind anomalies and the SST, I couple, use them together to train on a daily time scale, then that coupling between the ocean atmosphere on the intraseasonal time scales will be built in to give some memory to the system. And so that is what I am hoping to start with. But if there is more data available on soil moisture, I'd be happy to so question is, there is so far the soil moisture feedback, definitely it has some impact, but what drives whom is still not debatable, right? So is it passive or is it it is active? So we don't know. Even SST, we know that they are quite coupled, but who is driving what is not very clear, right? Because they affect each other. But if the coupling is clear, then I can use that as a because that is coupling is what is going to give memory to the system. Today's program. So,
Professor B.N.Goswami has given us some ideas to think about and what can be some useful projects based on based on the ML based weather forecasting especially in the context of Indian monsoon. So some ideas are here. So now your job is, I mean, as we discussed in that online meeting also, like the speakers will give some ideas. Your job is to discuss among yourself for these few days that we are here and try to come up with some kind of to identify maybe small groups of 3-4 like-minded people who are interested in those ideas. And so Professor Goswami is here for the first week, the first full week. So you can discuss further with him also during the lunch breaks, coffee breaks, etc. These few days, and maybe you can form some groups and to work on these things that were discussed. And so later in the next week, we will have these couple of sessions, maybe one session on these group project ideas, where whatever you have planned, you can just present in an informal way. So till then, as long as professor is here, you please discuss with him, discuss among yourself, and formalize the ideas, because we would really want to see some meaningful research collaborations coming out of this. Okay, so with that, let's say once again thank Professor B.N.Goswami for his thoughts. And let's close for today, and let's have a good period of rest and recreation, and some discussions also maybe over the dinner table, and we'll gather again tomorrow.